Okay, so last time we reached to this slide, which is part of lecture 1. So I'm going to call it lecture 1 and 2. This will be lecture 3. Okay, so that was introduction about vibration. We reached to the classification of vibration, which is one of the important things in the course. The classifications are free vibration, force vibration, and damped, linear vibration, and linear vibration, and there are other classification of vibration, but I focus on those things because this will be covered in the course. Okay, so chapter 2 is going to be about free vibration. Chapter 3 is about force vibration. Damped and undamped will be part of chapter 1 and chapter 2. And also, linear vibration. Linear vibration is also going to be part of chapter 1 and chapter 2 and chapter 3. And chapter 4 and 5 will be including free vibration, force vibration as well, but different degrees of freedom or different types of excitation. Okay, so as we said that vibration is about motion that is oscillatory type or periodic. Here we will talk about harmonic motion in details. Harmonic motion is one of the periodic motions. So periodic motion means that a motion that repeats itself in equal interval of time. So any motion that has this characteristics is called periodic. Harmonic is a simplest form, a simple form of periodic motion in which the motion is represented by sine or cosine, which are called harmonic functions. And this can be shown, this type of motion can be represented by Skacek mechanism. The Skacek mechanism is consisting of two elements, the rotating crank and the rod, okay, which is guided to move in one direction. Okay, so we have here this is the crank, which is rotating with angular speed, omega. Omega is the angular speed. And this is the rod, which has a slot. The connecting or the crank has a pin, as shown here with the red circle. This is a pin and the rod is slotted so that the pin can move in the slot and force the rod to oscillate up and down. Okay, so you can say that the crank is rotating in this direction with omega and cause oscillation to the rod, reciprocating motion. Okay, here just our model, which is the spring mass system, is added here, and you can see that the motion of the mass is equal to the motion of the rod. Okay. Okay, and you need an equilibrium position, which is when theta equal to 0, or the zero position when theta equal to 0. Okay, and theta, since omega is constant, the crank is rotating with constant angular speed, the angle made by the crank with the horizontal line, okay, this line is theta equal to omega t, because omega is constant, so that theta is omega t. Okay, you know this from dynamics, kinematics. Okay, the vertical motion of the road, you know, the road is guided. This is a guide here. So the road will be moving up and down, and you can find how much it will go up by you know, finding the vertical distance. So you can draw a right angle triangle here. Okay, this is 90 degrees. Then you can find the height. The crank has a length of A. This is the length of the crank, okay, which is from point O to point P. Okay, this point. So you can find the vertical, which is called here x, equal to A sine omega t. Okay, so this point of the pin is the vertical motion of the pin is equal to the motion of the rod, and it is can be shown as a sine wave, right? Because x equal to A sine omega t. So this is the plot of the mass attached to the rod at the top is making a sine wave. Okay, so when theta is 2 pi, this is 1 revolution. Okay, so regarding to the crank, the type of motion of the crank is rotation, but the type of motion of the mass is oscillation. Okay, you notice that the mass is not in rotation, the mass is in translation. So there is a relationship between the frequency of oscillation of the mass and the angular motion or angular speed of the crank, which are equal. For the omega for the crank is called angular speed, and omega for the mass is called frequency, and the unit, of course, of omega is radian per second. Okay, so for 1 revolution, you can put theta is equal to omega. Let's say that tau is time, okay, for 1 revolution. We call t equal to tau, which is the time to complete 1 revolution for the crank, equal to 2 pi. And then, as you can see, omega equal to 2 pi over tau, or you can find tau, which is equal to 2 pi over omega. Okay, so from the crank, we can move to the mass. That 1 complete revolution for the crank is 1 cycle of motion. Okay, this line should be up to here. Okay, to the end. From this is the start, and this is the finish. So this is 1 complete cycle. 1 complete cycle for the mass, it means it is moving from the 0 line when theta equal to 0, reaching to the top point. Okay, this line is reaching here to A, which is equal to the crank length. Okay, so when theta equal to 90, the crank will be vertical, and the rod will move to the full extent upward, and it reaching the maximum point. Okay, the mass is reaching maximum point, which is measured from the 0 line is equal to A. And then when the crank continue rotation and exceeded 90 degrees, then the mass will go down until and the crank is at 180 degrees, then it will come to zero. The mass will come to back to the zero line and then continues in the negative direction and reaches the maximum point in the negative direction when the angle is 270, right? And then go back to zero. So this is one complete cycle that start from equilibrium or from zero line back to the zero line. It's called one cycle. So the cycle can be also said from the peak at the negative to the peak at the negative is also one cycle. Okay, or any points. So the point and the corresponding point, or the maximum. Okay, the maximum point here and the maximum point here is also one cycle. So you can measure the cycle either from zero to the zero or from peak to peak. I mean, from one peak to the next peak. Okay, so that time required here is called tau. Time. Then the time to complete one cycle is called tau. Okay, so the motion of the mass is given by x equal to a sine omega t, and it is periodic. Okay, where a is the crank length. Omega is measured in radian per second. That is the one that we need for to substitute in the equation sine omega t, and it is called circular frequency. This is the technical name for omega for the mass. Okay, it is as I said, speed for the crank, but for the mass is the frequency, and it's called circular frequency given in radian per second. The frequency, as you know, also is given by hertz, which means cycles per second. Okay, so we have in one revolution that theta equal to 2 pi equal to omega tau. Okay, and then we can find omega is 2 pi over tau, and definition of a frequency is the reciprocal of the time of one complete cycle. So it is 1 over tau, which is shown here, F equal to 1 over tau. It's also called frequency, but this is in hertz, or it is given in cycles per second, which is known as hertz. Frequency is also has different names, or I mean different units. You can use cycles per minute, okay, or revolution per minute. RPM is one of the units also. But the common ones, we have the frequency is given in hertz. Okay, that is more known for frequency. For rotation, usually RPM is used, revolution per minute. And the one we need it in the unit we need in the equation is radian per second, the circular frequency. Okay, so we will find this is the motion or displacement is given by x equal to a sine omega t. So this is repeating itself. The motion is repeating itself every tau. Okay, as you can see from the figure. The same thing if you consider cosine. Cosine is also going to give you periodic motion. Okay, so we can find the velocity of the mass. Okay, this is also one of the important quantity, velocity, acceleration, and displacement, right? So you can find the velocity of the mass by differentiating x. So x dot is dx by dt. Okay, that's the meaning of x dot. and x equal to a sine omega t, then by taking the derivative with respect to time, we get omega a cosine omega t. Cosine is leading sine by 90 degrees, so you can write cosine as sine omega t plus pi over 2. So that the velocity becomes omega a sine omega t. Okay, so you can see that velocity, here there is sine and here there is sine, but for velocity it is, instead of just sine omega t, it is sine omega t plus pi over 2, which means the velocity is leading by 90 degrees. Those are vector quantities, the displacement, velocity, acceleration are vector quantities, and then direction, or leading or lagging, is also important. The acceleration is equal to the second derivative of x, t square x by dt squared. So this will be, which is equal to, you can use, it is the derivative of velocity, so it is dx by dt, dv by dt, but since I'm using x dot for velocity, I will just keep this as d square x by dt squared. So this becomes minus, derivative of cosine is minus sine. So there is minus omega square a sine omega t. The minus and the sine, it means that you can use sine omega t plus pi. Okay, and you take out the minus. Okay, the minus is included in the sine now. So omega square a sine omega t plus pi, which is pi, when you compare x double dot, which is the acceleration, with x, you can see that it is leading, acceleration is leading displacement by 180 degrees. So those are the figures for displacement. It is a sine wave, and x dot is a cosine wave, and this is the acceleration, which is minus sine. Okay, so when the mass reaches the maximum point here, then the velocity is 0, right? And this is, we know this, that at maximum displacement, the velocity is 0. So at the top point, the velocity of the mass is 0. And when it reaches the maximum on the other side here, again, the velocity is 0. And there is a phase shift. So this is the this wave and this wave are the same, except that this is moving 90 degrees ahead, or it is occurring at 90 degrees before x. So x dot, okay, is starting from here, right, which is cosine. So this is 90 degrees difference. So this is why it is leading. And the acceleration, it is when x is positive, okay, the acceleration is negative. Okay, and when the x is negative, this is positive. The acceleration is positive. And you can represent since they are vectors, so we can say this is vector representation of x dot and x double dot, which means the vector representation of displacement, velocity, and acceleration. Okay, so x at an angle theta, which is omega t, and 90 degrees to x is x dot, and 180 degrees to x is x double dot. those are the three quantities of dynamics or kinematics, to be more specific, of the mass and their oscillations. Okay, so already I talked about the relationship. This is the relationship of displacement, velocity, and acceleration. So this is just to enlighten on, focus on some other things like the peak value. Okay, the peak value for x is a, which is equal to the crank length of the Scotch mechanism. Okay, measured from equilibrium. So the peak is the maximum measured from the zero line or the equilibrium line. Okay, so this is A, measured from here, not from minus A to A. Okay, that is called peak to peak. Okay, so the peak is the maximum. You measure with, you measure the position of the mass from a point, a reference point, which is the zero line. Okay, sometimes for the spring mass system, it is called equilibrium line. The velocity, the peak value is equal to omega A, and you can see this from the equation that x dot is omega A cosine omega t. So omega A is the peak value of the velocity. So that's the peak velocity from 0 to here. It is omega A. And for the acceleration, the peak value, again from the equation of x double dot, we have minus omega square A. So omega square A is the peak acceleration, peak value. So here it is, from here to here is omega square A. That is the peak value of the acceleration. So the value, if measuring, if you are using measurements, sensors to measure the vibration, you can measure. There are sensors that measure displacement, and there are sensors that measure velocity, and there are sensors that measure acceleration. And you can see how is those values are changing depending on the value of omega. Okay, so A, let's say it is in millimeter and omega in radian per second. Then at high frequencies, A is very small, but acceleration is very, very high because it is omega square A. Okay, so suppose we have omega equal to 100, okay, 100 radian per second. Okay, then 100 squared, it is 10,000. So if A is 1 millimeter, then this will be 10 meter per second squared. Okay, so some of the applications you need to measure acceleration because A is very small. That amplitude is very small. You need to measure the acceleration, and that is related to measurement. We will talk about in chapter 3 about some sensors or vibration measuring instruments. Okay, so what you can notice from the relationship between x and x double dot, if I go back here, you can write x double dot as well equal to minus omega squared, and A sine omega t is what? Is x. So you can write x double dot equal to minus omega square x. This is called the condition for harmonic motion. So all periodic functions, harmonic belongs to periodic functions or motion and should satisfy this condition. So not all periodic functions satisfy this condition, that the second derivative of the original motion is directly proportional with the negative motion. Okay, which means x double dot is directly proportional with minus x. This is the condition for harmonic motion. And when you take out the proportionality, you get that x double dot equal to minus omega square x. Omega is the frequency. It is in radian per second. An example of a non-harmonic periodic motion is this. Let me just change the color. Okay, this is periodic because it is changing or repeating its motion every tau. Okay, this is one. Okay, we can have this is also periodic motion. Okay, because it is repeating itself every tau. But those are not harmonic. Periodic but not harmonic. And you can see if you write the equation for x from 0 to tau, if this is the peak value is a, then you can write x equal to a over tau times t, which is the equation of a straight line. And this is valid for t greater than or equal to 0, less than or equal to tau. Okay, but when you find the derivative, x dot is a over tau. And when you try to find the acceleration, this is 0 in this interval. So it is not satisfying, not harmonic.
دكتور
Okay, the same thing. Yeah.
يعني بس الساينوسويدال functions harmonic.
Sinusoidal functions, sine and cosine, and the complex form of sine and cosine, which is the exponential form. Okay, this is not harmonic as well. Okay, those are the harmonic functions are sine and cosine, and also you can write ei omega t is also harmonic because ei omega t is the complex form of writing sine and cosine, because this is equal to cosine omega t plus I sine omega t. This is also harmonic. Okay, because the derivative of ei, if we let x equal to ei omega t, okay, you can write, you put a here, then x dot equal to a derivative of ei omega t with respect to time is I omega ei omega t, and second derivative is equal to a times I omega squared ei omega t. Okay, so this becomes minus, because I is square root of minus 1. So this square root of minus 1 squared is minus 1. So it is minus a omega square ei omega t, which is equal to minus omega square x. So this is also harmonic. But ei omega t is the combination of sine and cosine. So those are the harmonic functions. Okay, so that's the condition for harmonic motion. So the difficulty in periodic motion in general, for example, this one, sine or cosine can be evaluated for any time with the same equation. Just A sine omega t is valid for all time. But as you can see for this periodic motion, it has to be defined interval by interval. So the equation I gave here, and this is only valid for the interval from 0 to tau. If you want the equation from tau to 2 tau, you cannot use this equation. That is only valid from 0 to tau. So you have to define for the second interval is from tau. Let's say we can remove the equality if you want. Less than or equal to 2 tau, then x is different. Not equal to the a over tau t. You have to find the equation of a straight line, which is the same slope, a over tau multiply by e minus tau plus 0. So when t equal to tau, it is 0. When t equal to 2 tau, it is a. Okay, so again, this is not the same equation. For each interval, you have to define an equation of motion or equation that represent the displacement. The same thing, of course, for all other periodic functions. This is also, you need to define interval by interval. So one way of representing periodic functions or motions is using Fourier series. Okay, which is showed by Fourier, which is a French mathematician. Okay, he suggested to that any periodic function can be represented by sine and cosine. So he wrote a series, okay, a series function that can represent any periodic motion, which is written as x of t. This is the given periodic motion. Okay, let's say function in general. Equal to a0 over 2 plus a1 cosine omega 1t plus a2 cosine omega 2t, and it continues to infinity, plus b1 sine omega 1t plus b2 sine omega 2t plus b3 sine omega 3 tt, and continues to infinity. What is omega 1, omega 2, and so on? Omega 1 is 2 pi over tau, and we know this from the previous topic we talked about. Okay, that the frequency is defined as 2 pi over tau, and tau is the period of one cycle, or the time for one cycle. We call it period of oscillation. So the given periodic function x, or also the time is given for one cycle, tau is given. Then omega 2 is 2 times omega 1. In general, omega n is n, omega 1 and n is integer equal to 2, 3, 4, and so on. So it is n is an integer value, and omega n is n omega 1. Okay, and here is an just for as index. In general, you can write this as as a summation, you can use the summation from n equal 1 to infinity of an cosine omega n t. I can add omega 0 is 0. Okay, or we can just expand this. We put the 0 alone, equal to a0 over 2 plus this, plus b n sine omega n t. Okay, so a0 over 2 is the first term. The other terms are put in the summation from 1 to infinity of an cosine omega nt plus bn sine omega nt. Now infinity is, you will wonder, we cannot reach to infinity, but the good thing about this series, it converges with a few number of terms, so that with a few number of terms you can represent with good approximation the original, the given periodic functions. So in general, any periodic function can be represented by Fourier series. It is called Fourier series, named after the person Fourier. Okay, so what are the unknown things in the series? Of course, x is the given. Omega 1 is given based on the given value of tau, or you can calculate omega 1 based on the given value tau. And then omega n is equal to n times omega 1. So the unknowns are the coefficients of the series. Okay, those a0, a1, a0, a1, a2, and b1, b2, those are called Fourier series coefficients, are unknown. So once we find them, we find the series. And the time is the independent variable. So this is not an unknown. Okay, you can substitute for any value of t to find x. So we need to determine the Fourier series coefficients by of the series, using the properties of sine and cosine. Sine and cosine are, when integrated over one period, they cancel out. Okay, so if you integrate, if you have a sine wave over one period from 0 to tau, this is a plus area, this is negative area. So the integration of sine omega t dt from 0 to tau, or over one period, does not, we don't have to from 0 to, say the limit from 0 to tau, from limit as far as the limit is over one cycle, is 0. Okay, the same thing for cosine from 0 to tau is also equal to 0. Now let's say we have, this is omega 1. If you have omega 2, it means 2 omega 1. So within this, you will have 2 cycles, right? 2 cycles of sine. So this will be integration of sine omega 2, which is 2 omega 1 t dt from 0 to tau. Okay, this is the same limit from 0 to tau is equal to 0 also, because here plus and a minus minus. The same thing for the cosine. So in general, integration of sine omega n t dt equal to 0 from 0 to tau. Integration from 0 to tau of cosine omega n t dt also equal to 0. So one way, if you integrate both sides of the series from 0 to tau, then this will be, when you integrate, this will be 0, and all terms will be 0. All terms that contain sine and cosine will be 0, and this way you can find A0. The other properties of sine and cosine is that they are called orthogonal functions. يعني they are نقول عنهم متعامدين. There is a phase difference between sine and cosine is 90 degrees. So whenever you have a term cosine multiplied by sine, it will be always 0 as far as you integrate over one period. Here it is shown minus tau over 2 to tau over 2, or from 0 to tau is the same. Okay, as far as you're integrating over one period. So sine and cosine, the integration of sine and cosine is always equal to 0, and n, those are the integers. N is 1, 2, and so on. M is also integer, 1, 2, and so on. Those are integers. So whenever they are, there is a term sine multiplied by cosine, it will cancel out. So what you can do is multiply the series both sides by cosine omega mt, not n, m. And then the one with the term of bn will cancel out. And cosine times cosine, it depends on the value of the integer. Cosine omega nt multiplied by cosine omega mt, n and m are equal, then this becomes cosine squared. And cosine squared, integration of cosine squared is not 0. But when the n and m are not equal, the integration of such functions will be 0. So when n equal to m, then the integration of this will reduce to tau over 2. And the same thing for sine multiplied by sine omega nt multiplied by sine omega mt, this will have the same thing, 0 when m not equal to n, and tau over 2 if m equal to n. Those are properties of sine and cosine. You can use them to find the coefficients of the series. صعبة لا؟ واضح؟ Clear? So you can multiply the series both sides by cosine omega mt and integrate both sides, then you can find an. And then multiply by sine omega mt both sides and integrate, you will cancel out an and find bn. So the resulting equations, okay, those are the two simple equations you will have at the end, including A0. That an is equal to 2 over tau, integration from 0 to tau, if you want to change the limits, of x of t cosine omega nt dt. So as simple as that, using those properties, the properties of sine and cosine, you can have two equations that can be used to evaluate the constant. If you want to find A0 is when you use omega 0 is 0. So cosine 0 is 1 and sine 0 is 0. So there is no B0, there is only A0. Okay, you can add this to the family of the frequencies. Omega 0 is 0, omega 1 is 2 pi over tau, and omega n is n omega 1. So A0 is 2 over tau integration of x of t only. And A1 or An in general is this equation. The same thing for Bn is 2 over tau integration from 0 to tau, or from minus tau over 2 to tau over 2 of x of t sine omega n t. This integration of the functions cosine and sine can be further simplified. Okay, you don't have to evaluate the integrals if you know that the function of x is even or odd. Okay, so for even and odd function, we can simplify the integration. If you have x, okay, this is for x equal to e for even. What is the meaning of even? Okay, even function, if you have an expression of f of x, then f of minus x equal to f of x. This is called even. And odd function is f of minus x equal to minus f of x. It's called even. It is called odd. So when you have x is even, sine is odd or even? Sine is odd. Yes. And cosine is even. Okay, sine, if you plot an example of the even is the cosine. So if you continue on the other side, so if this is minus t, it is same as you get the same value of x at t. So they are equal in sign, in the sign of the function is the same. For example of odd is the sign. So if you continue on the other side, at minus t, it is equal to minus of at t. So they are equal, but they have opposite sign, opposite الإشارة يعني. Opposite sign. We have here minus, here a plus. This is called odd. So if x is even, then x multiplied by sine omega n t, and their integration is 0, which is equal to this is equal to Bn, that Bn is 0. Okay, when x equal to odd, then An equal to 0. Okay, because An is cosine, integration of x cosine. When x is odd, then An equal to 0, but not necessarily A0. Okay, A0 might be not 0. Okay, although An is 0, but A0 might be not 0. So what is the meaning of A0? Okay, this is the last thing I will talk about. A0 is the average of the function. So here is an example. This example is about this function is called sawtooth. يعني شكلها شكل sawtooth. Its average is not zero. That A0 is not zero. That's called average. If you have a function that is changing above and below, for example, we have okay, this average A0 is zero here because the average is zero. Okay, if you have a function like this, A0 is not zero because the average is somewhere above the zero line. Okay, if you have a function, this last thing I will do. Okay, if you have a function like this is also periodic. So A0 here is zero because there is positive, negative areas which are equal. Okay, so the same thing here. Okay, we will come back to this example and see how we can apply the Fourier series to find the representation of the function, which is periodic function, using the Fourier series. Okay, any questions?
دكتور بنحل بس في التوتوريال
بنحل أسئلة من التوتوريال؟ هاي سؤالك؟
لا يعني بس محاضرة التوتوريال بنحل أسئلة الدكتور شوي نبي نشوف أسئلة عشان نفهم شوي زود.
اي طبعا لازم، بس لازم اخلص الموضوع مال يعني اشرح الموضوع على اساس اقدر احل اسئله.
إن شاء الله.
اوكي، فركز على الفكره المطلوبه في المحاضره الجايه ان شاء الله، بعدين بنشوف شلون نحل الاسئله.
إن شاء الله. يعطيك العافية.
المحاضره الجايه نكمل الشابتر. يا سلام.